Hey again, everyone. This is the Thursday video. We're going to talk about Coulomb's law. That is the way to calculate the electrostatic force of attraction or repulsion between different objects. Charles Coulomb, again, his name is granted to the property of charge, so obviously he's an important guy with electrostatics. Kind of like Isaac Newton, who experimented with gravity. Charles Coulomb experimented with the forces involved with electric charge. He noticed that obviously the different charges repel and the like charges repelled and the unlike charges attracted. Back in the late 1700s, he conducted experiments with metal spheres to try and see what the relationship between charge and force was. He noticed that the amount of force between two charges was directly impacted by the amount of charge, but he saw that there's also an inverse squared relationship between force and the distance between those two charges. I'm going to show you a simulation illustrating this idea. For example, over here we have one charge of 2 microcoulombs. That's what this mu symbol means before the C. That means 10 to the negative 6 microcoulombs. And over here, charge number 2, I made it negative, but it's still 2 microcoulombs. So the same amount of charge between these two. And we're looking at a force of attraction of around 80 newtons. But look, if I take charge number 1 and I double its charge, I'll make it 4 nanocoulombs. That charge is now about 180. So we about doubled the force between the two charges by doubling the charge. Well, let me bring it back down to 2 and 2. Again, we're looking at about 80 newtons of charge on either one. Doesn't matter which one you're looking at. They each feel the same force of attraction. This actually is an example of Newton's third law. Action and reaction forces are equal in strength and opposite in direction. But let me take this charge number 2, instead of making it 2 centimeters away, I will double that distance and bring it 4 centimeters away. Again, we have 80 newtons right now. Doubling the distance to about 4 centimeters, well, now we're looking at about 20 newtons. So I've doubled the distance, but I've reduced the force not by cutting it in half, but by cutting it into about a fourth of what it used to be. We can do that in reverse as well. Looking 4 centimeters apart, we have about 20 newtons. I have the distance. So you say, oh, well, getting closer, the force should go up. Yeah, but not by doubling. Bring it back to about 2, and we're looking at about 80 newtons. So 20 to 80 by doubling or halving the distance. So then Charles Coulomb says, oh, well, I guess the relationship between charges is direct with the amount of charge, but not so with the distance between them. So he makes an equation relating all this information. He calls it, well, I don't know if he called it Coulomb's law, but it is known as Coulomb's law. And the equation looks like this as soon as my screen loads up. The amount of force, electrostatic force, between two objects is equal to the two charges multiplied together, Q1 and Q2, divided out the distance between them squared. That's what this R means. It's the distance of separation. But then you have to multiply that by some constant, and that constant is known as Coulomb's constant, the variable K. K, as a constant, has a value. It is 8.99 times 10 to the 9 Newton meter squared per Coulomb squared. Huge number, but that's just so you get the right amount of newtons after you combine these charges and dividing out these distances of separation. This equation should look familiar to the Regents physics students. I hope you see some similarities between this one and another one from Isaac Newton.